Hello, my friends. It's MoNaCo here. We are starting our 5th homework lecture video on our acids and base unit. We're going to be talking about the alternate acid-base theory in this lecture. In the previous lecture, we did the Arrhenius theory, how Arrhenius acids produce H plus and Arrhenius bases produce OH negative as the ions in solution. That's what makes them acids and bases. But that theory did not explain why ammonia, NH3, is considered a base, and some other things which don't begin with hydrogen in their formulas are considered acids. So this alternate acid-base theory will explain such. It's the Bronsted-Lowry theory. And that's what we're going to get into here, because we know the Arrhenius explains the behavior of most acids and bases. This theory explains the exceptions. This is Bronsted-Lowry is the name of the theory. We refer to it as the alternate acid-base theory because it explains the exceptions. So let's get into our notes here. So the alternate acid-base theory, also known as the Bronsted-Lowry theory, this theory explains the behavior of weak acids and weak bases. So Arrhenius was good for the strong acids and bases, which deionize or dissociate completely. This explains those ones that don't do that so well. So Bronsted-Lowry acids are the proton donors. So Bronsted-Lowry acid donates H plus to a Bronsted-Lowry base. So acids donate H plus somehow. They get to be able to donate H plus. So circle the Bronsted-Lowry acid below. So we have HCl plus H2O becoming H3O plus and Cl negative. So we got to think, what donated the H plus? Well, the H plus must have come from this HCl. So there it would be our acid. And therefore the base, well, would be whatever accepts it. Bronsted-Lowry bases are the proton acceptors. Bronsted-Lowry base accepts H plus from the Bronsted-Lowry acid. So H2O plus NH3 making NH4 plus and OH negative. So we're going to circle the Bronsted-Lowry base because it accepted the H plus. Accepting the H plus was this guy. That's the base in that case. So we have the Bronsted-Lowry acid, which gave up the H plus, and we have the base, which took the H plus. And if we see at the end here, we have an OH, so that we know that a base was in play. Bronsted-Lowry conjugate pairs. This stuff is a little bit over our heads necessarily sometimes in Regents. I haven't seen conjugate pairs asked in quite some time, but basically, Bronsted-Lowry conjugate pair is the acid and the base that it produces, or the base and the conjugate acid. So this is the Bronsted-Lowry acid because it is a proton donor. And whatever is created as a result is its conjugate base, like whatever was used, like whatever's left over. So we can think of that as left over, the leftover stuff is the conjugate base. The base was easy to recognize because it accepted the proton. That was this side, and this is the leftover portion of it. So the conjugate acid and the conjugate base is what's left over on the opposite side of the reaction from the Bronsted-Lowry acid and base doing its job. Okay. Don't worry about that too much. I probably won't put it on our test. Using brackets and the key from the example on the previous page, indicate the conjugate pairs in the equations below. So we got to think about some things here. Bronsted-Lowry acids and bases. So the acids are proton proton donors, bases are proton acceptors. So here is the Bronsted-Lowry acid. So that's the base, because it accepted the H plus, and then that would make this the water, the acid, because it gave up the H plus. Now let's make sure that we label the conjugate acid and conjugate base properly. Base goes with the conjugate acid, acid goes with the conjugate base. So the base goes with the conjugate acid, the acid goes with the conjugate base. So we have to look and see which species is donating protons and which is accepting them. So that's why I do it. So which is donating? So acids donate, and H Cl became Cl, so that was the acid, which goes with its conjugate base. Okay, simple enough. Which probably leaves water to be the base with its conjugate acid. It's kind of just opposite using this bracket system to identify. I won't make you do that on the test, I don't believe. So let's find the acids are proton donors. HI became I, so that must have been the acid. It lost a proton. It makes the donor, so that makes this the conjugate base. And then we've got HOH and H3O. So HOH became H3O, so that was a base and its conjugate acid. Back and forth, back and forth. That's kind of how this works. Let's do the last one here. HNO3 became NO3. So that was the acid that donated. That's the conjugate base that was produced, which leaves H2O and H3O be the base and the conjugate acid. Okay. You're noticing here in this case, I hope, that water is acting as a base in these situations. That is one of the underpinnings of this alternate acid-base theory, is that water kind of swings both ways. It could be an acid or a base because it's got H's and OH's in it. I don't know. Bronsted-Lowry theory, all you really have to know is that acids are proton donors, bases are proton accessors. Amphoteric, amphiprotic, substance that can act like an acid or a base. This is what I just mentioned when I said water. Amphoteric is the word that we use that means that water can play both games. Water is amphoteric, see below, because H2O plus another H2O, I could get H3O on one side, so that would be the acid and its conjugate base there. But then if I look at this H2O, I got the base and the conjugate, oops, I made this back, conjugate base, conjugate acid, acid, and base. Anyways, either way, water's kind of playing both sides of the game here. Which of the following substances is amphoteric? Which thing could both give or take protons? It's this one right here. It has one proton to give, and it looks like it's got a negative sign, so it has some to take as well. Nothing else in this chart here could go both ways. Identifying the main points of alternate acid-base theory, and these are the two things I really need you to know. Acids and bases. Acids are H plus donors, bases are H plus acceptors. That is the major underpinning and the takeaway from this video. Acids and bases have conjugate pairs, kind of a side note. Thanks for watching.